Okay, we're going to be extending our stuff on surds. You should have done exercises in all of these, being able to solve these sorts of problems by multiplying inside the surd to create a single square root. If you wind up with surds in the denominator of any rational function, it's considered bad form. It's not the logical place for them to be. So we're going to explore the techniques for turning the denominator into a rational or even a completely simplified polynomial. So it doesn't have any square roots in the denominator. I'm just going to go quickly and solve these and expand these brackets out, which is the purpose of this is to learn the pattern that we need for this third line. So if I go through, we get a squared plus is the first, outer is a times 1, inner is 1 times a, so that gives me a 2a, and 1 times 1 is a plus 1. The second one, we get a b squared. We get a minus b on the outer. On the inner, we get a plus b, so they disappear. Plus 1 minus 1 gives me a negative 1. Carry on through, we get c squared. You get 2c from the outside and 2c from the inside, so it's plus 4c, and then plus 4 on the inside. Do d squared, plus 2d, but minus 2d gives us nothing, minus 4. 2e times 2e is 4e squared, plus 6e, plus 6e, plus 9. And this one down here is 2f times 2f is 4f squared, minus 6f, plus 6f, nothing. 3 minus 3 gives me minus 9. And what you should really recognise from this is we've got some standard patterns of things that happen. If I've got a plus b squared, we got a times a squared. We then get an a times a b and a b times an a, which are both the same, so it's a 2ab plus b squared. These are standard ones. If you've been into a local school, you'll have seen these plastered all over the walls in a maths room. The important one is this last one. And the last one, so this last one is actually an important one. And what you get is you get a times a is a squared. A times minus b is minus ab, times an b times an a, which is plus ab, nothing. And then I get a minus b squared. And this has a special name. It's called the difference of two squares. And it's an important pattern because it allows us to actually remove the square root in these expressions. And if you see difference of two squares, it's often called dots. Okay, so just to do a factorising, factorise these. Nearly all of these actually follow difference of two squares pattern. So this first one, we've got a c and an 81. So if this is c squared, we're going to go back. We get c plus, what's the square root of 81? 9. And c minus 9. Let's move down to this one. Look at the numbers and we get 4p, because 4p squared is going to be, give me 16p squared. 5q, and 5q will give me the 25. And the signs, because I want the 20pq to disappear by adding and subtracting, one is positive and one is negative. The negative always goes on a term which has the subtract in front of it. So if you've got a q squared term with a minus, one of its q terms must be negative. Let's go for the last one, 11e and 11e. 169 is 13 squared. And they've got opposite signs, so one's plus and one's negative. So let's just check we've got those three correct. There are three correct answers. Hey. So how do we apply it to this next pattern? Well, what we realise is if I'm going to do a bracket, the square root bit in here, so let's have a look at one of these square ones where we're squaring the bracket out. So I've got a square root of 11. There's something funny with this setup of Office. Sorry. So we've got a square root of 14 plus 1 square root of 14 minus 1. And what we want to do is multiply this out. So minus 14, square root of 14 times the square root of 14, square root of 14 squared, which is 14. We get a minus root 14, and then plus a root 14. So there's nothing there. And then we get 1 times a minus 1, which is a minus 1. Gives me 14 minus 1, which is 13. Quick play again with the second one. Square root of 16 plus 2. Square root of 16 minus 2 gives me the square root of, sorry, don't need the square root bit. Gives me 16 minus 2 root 16 plus 2 root 16, don't need it, plus 2 times minus 2 is minus 4, gives me a solution 12. So just ask a little question to yourself. What would you do if one of my brackets had square root of 17 and I had a minus 3? What would the other bracket be so that I can completely turn this into a rational number? No irrational parts at all. What would need to go in there? Now this is a powerful technique. There's an area of maths called complex numbers, and in complex numbers this dots leads to something called a conjugate pair. And we're using the same sort of pattern. We're looking for a pattern where the first thing that we want that to be squared. So that gets rid of this 70 at the square root. We need the second bracket to have the same factor. So we get a minus 3 and a plus 3. And then we're going to get a number off in the end. So the 17 minus 9 gives me an answer 8. So I now have a nice little pattern to use for expanding brackets. That means I can do the bottom line now. So if I'm looking at my denominator, I've got an 8 plus a square root of 2. I can say I'm going to multiply this bottom by its partner. So 8 and a square root of 2. Now it doesn't matter which one you actually use. One of them just has to have a negative in it. Because of the way around it's written, I would put the minus on the square root. So that I'm not changing my fraction, I do the same thing to the numerator. And when we multiply through on the bottom, what we get is we get 8 eighths of 64 minus root 2, 2. Don't forget 8 times minus root 2 plus 8 root 2. That's what's disappeared. Don't forget it though. Don't get lazy with this. So we also have in our mind 8 multiplied by minus root 2. and 8 times plus root 2, and they both equal 0. That's why that disappears. On the numerator, I need to do some calculation. I'm going to use a calculator for it. There's no problem with us using a calculator at this time. Multiply by 8 is 992. And I would like to subtract from that 124 times the square root of 2. This gives me 992 minus 124 square root of 2 all over 62. And I don't know if that will divide. Well, that does. That gives me 16. So denominator, that's part over 62, 992 over 62 simplifies, plus 24 root 2, 124 over 62. So this goes 16 times, plus 2 square root of 2. That goes 16 plus 2, press the square root button, 2. Check it. What have they done to theirs then? Done 24. Might be they've just got things the other way around. I do have a quick way to check this. 8 plus square root of 2. The way I'm checking it is I've got a Casio calculator which does surds for me. Oh, it says minus. Where did I get? Oh, minus. That's why. That's a minus, not a plus. Minus, not a plus. Do be careful about signs because it does introduce sign changes. Let's check again. There we go. Now it's correct. Let's do another one quickly. Let's try the 244. You're not normally asked to do things quite as bad as this, but 244 all divided by 8 plus the root 3. What we're going to do is we're going to multiply both sides, top and bottom, by the conjugate pair, or the partner. So there's a plus, this one becomes minus, so 8 minus root 3. So what we're actually doing is we're multiplying one fraction by another fraction where the numerator and denominator are the same. So we're multiplying by 1 effectively. 244 times 8 is 1952 minus 244 square root of 3. 8 eighths 64 again. And we're going to subtract from that 3. Remembering along the way we've got 8 times minus root 3, and we've got 8 times plus root 3, which go together to give us 0. So we've got 1952 over 61 minus 244 divided by 61 root 3. I'm not sure about the 1592 divided by 61, but it will simplify. That goes to 32 minus that, which is going to be 4 root 3. 32 minus, click the square root button, 3, sorry I forgot to put 4 before the square root, and check this, it's correct. These last ones up here, the first part with them is to get a common denominator. So let's do the 6 over root 2 plus 12 over root 6. I would probably go cross multiply to give me denominators that work. So I've now got 6 square root 2, 6 square root 6, plus 12 square root 2, all divided by square root of 2 times the square root of 6. These ones going on the numerator, we get 18. Oh no, we don't get 18 at all. Let's look at these top. Let's do the bottom. So we get square root of 12 on the bottom. Plus 12 root 2 over the square root of 12. And we need to multiply top and bottom by the root of 12. This time we do not need to use the conjugate trick. What we're doing is we're multiplying top and bottom by 12, because 6 times 2 is 12. We've got a square root of 12 on the bottom, square root of 12. So this is going to become 12 on the denominator. Square root of 6 times square root of 12 is the square root of 72. Plus 12 times the square root of 24. And we're looking now in these about our factorising. So let's think about factorising. 72 goes 2 and 36 goes 4, 2, 2, 9, 3, 3. So we've got a square root of 2 left inside on the 72. And we've got the 2, 3. So we've got 36 square root 2 on the first one, plus 12 square root of 24 is 8 times 3. This is 2 and 4, 2, 2. So we have another square root of 6 over here. Got 6, 2. We've got 12. And 12 times a root 2 root 6, so we've got a 2 there. 12 times 2 is 24, times the square root of 3 and 2, because these two can't be split, all divided by 12, which gives me 3 root 2 plus 2 root 6, and that was that one. 3 square root 2 plus 2 square root 6. Okay. This top line is just put that, multiply that by root 5, or multiply top by 5. So I'll do one of them. Let's go for the other one. So I've got 15 over root 5 minus square root of 20. And what I can do is, I want to get rid of this root 5 on the bottom there anyway. So I've got 15 square root 5 over 5 minus square root of 20. Cancel there. Next to it, so I'm doing the same idea as I did before, same layout. So first thing I'm going to do is I'm going to simplify this one into 15 square root 5 over square root 5 square root 5 minus root 20. That gives me 15 over 5 times the square root of 5 minus 20, remember, is 4 and 5, so that's 2, 2, 5. So we can now actually take a 2 root 5 out, and we get 3 root 5 minus 2 root 5. Remember, any piece of algebra, so I could call that f. f. 3f minus 2f gives me 1f. My result is square root of 5. There you go. And that's how you can do all that stuff about rationalizing fractions. Okay, so